And boom. Okay, guys, what I'd like to do is I'd like to spend just a moment with you and do a 30,000-foot pass at chapter 4. If you're not familiar with the concept, it means that we're sort of looking down from on high and getting a sense of what we have coming at us in chapter 4. I would propose to you again, because you're trying to figure out how to read science texts and you're quickly finding out that they don't have plots or vampires and you don't know how to read them. Guys, starting in chapter 4 on page 115, you'll notice that there's the title. And it's easy to read over those and just sort of take them for granted, but I think if we pause for a second, we may learn something. So guys, in chapter 4, given the title, where is all of the chemistry that we are about to learn about going to take place? In water. Guys, aqueous chemistry means the chemistry of things that are in water. So what you're going to find out is that this chapter 4 not only gives us good background into water-based chemistry, but also what it's going to do is it's going to lay out for us some things that we will do at the end of the year. It turns out, and you'll see this in a minute, that the way this chapter lays out is it provides some really good background. We're going to talk about electrolytes, non-electrolytes, and solubility. Thus the solubility table that you were to have summarized and brought with you. Then what we're going to do, guys, and let's just do this together. So turning the page, you'll notice that it talks about general properties. If you've started the outline, you know this. And it talks about electrolytes, ionic compounds, turning over again, molecular compounds. Then, guys, it gets into strong and weak electrolytes. That we're going to cover right now. Then watch this. 4.2 is precipitation reactions. We're going to do that today. Then changing back to page 124, 4.3 is acid-base reactions. We are going to cover that next time. But guys, we are only going to cover this at an extremely superficial level so that we can talk about acids and bases superficially and we know what we're talking about. Understand that obviously doesn't mean this isn't important. What this means, guys, is we are going to spend 6 weeks on this in March. Chapters 16 and 17 are all about acids, bases, buffers, and equilibria, and titration. Guys, this is the hardest, biggest, craziest, nastiest, most important thing we're going to cover this year. And we're going to cover it on Wednesday in about 15 minutes. And then we're literally going to spend 5 to 6 weeks on it at the end of the year. Then, guys, turning the pages again, when you get back to 4.4, I don't know where it went, 4.4, 131. Guys, this sounds crazy. We're going to talk about oxidation reduction reactions on Friday, again, in about 15 or 20 minutes. When we cover this again for real, which is chapter 20, we're done for the year. And it's going to go like that. And just mental note, when we cover chapter 20, which is oxidation reduction reactions, we're done for the year. That's it. We're going to spend 4 class periods in oxidation reduction reactions, and then we're done. It will be all over when we get here. And guys, blink, and it's going to happen. Then, guys, you'll notice that as you continue to page back through the chapter, we'll get into 4.5 just briefly about concentrations of solutions. That's just molarity, and you already know it. But we'll touch on it briefly when we need to. So guys, the way that this is going to go is today we're going to talk about the foundational stuff that you need to know about aqueous chemistry. We're going to talk about strong, weak, and non-electrolytes. Then when we're done with that, we're going to talk about precipitation reactions, and we're going to talk about complete molecular, complete ionic, net ionic, and spectator ions as that relates to writing chemical equations. We're going to be drawing pictures. We're going to be digging into this chemistry. When we're done with that, we're done. Wednesday will be acids and bases. Friday will be redox chemistry. And then when I see you again the following Wednesday, we'll take our first test. Brandon, you had a question?
Yeah, so we're just skimming stuff right now and we're jumping.
Exactly. Yep. All right. So guys, getting started, here we go. When we talk about precipitation reactions, remember that's not where we're starting today, right? We're going to start with the foundational stuff with aqueous chemistry, and then we're going to wrap up with precipitation reactions. So let's talk foundational chemistry first. Again, guys, all of this is happening in water. So when we talk about things that are in water, the first thing that we've got to talk about is how do things dissolve in water? Do they do it well? Do they do it really well? Or do they do it not at all? And those are the things we need to start with as we talk about solutions. So guys, when we talk about solutions, I don't think we need to mention this, but we will. Guys, there's two parts to a solution, right? What are the two parts of a solution? Solute and solvent. The solvent is the thing that's doing the dissolving. For this unit, what will that be? Water, because this is aqueous chemistry. And then our solute is the thing that's trying to dissolve in water. So with that said, guys, this can happen one of two ways. Again, the idea here is that these things are dissolving. And so if something dissolves in water, it can do it as what is called a non-electrolyte. That simply means that the solution does not conduct electricity. So guys, this is going to come up in your notes in a second, but let's talk about it foundationally. In order for a solution to conduct electricity, what has to be present? Charged particles. Okay? There has to be something in there that's charged. So guys, let's make sure that we're all really clear on this so we understand how this works. And I wasn't really planning on doing this, but I can just a second. So let's get all the ions out of here. Okay, so guys, we now have a bucket of water. Does this conduct electricity? No. Water does not conduct electricity. So if you were standing in a lake of distilled water and that lake got hit by lightning, you'd be fine. Water does not conduct electricity. Why not? Because these dudes aren't charged. This is a molecule, hydrogen and oxygen bonded together to form water. There are no charged particles, therefore it cannot conduct. Now let's talk about things dissolving into that water. So first of all, guys, if we have a non-electrolyte, does it dissolve into the water? Absolutely. But what it doesn't do is form charged particles. And guys, we call these non-electrolytes. So let me give it to you and then we'll talk about it. So guys, non-electrolytes are things that do dissolve, but they don't form ions. Their solutes are soluble, but they don't form ions in solution, and therefore they don't conduct. So guys, understand, water itself does not conduct electricity. When we dissolve things in water, there's the possibility that it could conduct. Get this down and then we'll talk. There's the possibility that it could conduct. But guys, understand that if something dissolves in water and doesn't form ions, it will not conduct electricity. So guys, we need to talk about this while we're going. I understand that you have questions, and I love that you're curious, and I love that you want to engage. But you also, I know that Brandon and Matt both have questions, but understand that I'm going to reserve the right to bring you into the conversation where it's appropriate given everybody's needs. So don't get impatient with me if I don't do the immediate, yes, what do you want to talk about? I'm still going to control this conversation and allow everybody to move forward. I see you, and I am ignoring you, but eventually I'll invite you into the conversation. But I want us to get to places where it makes sense to break and discuss things. So with that said, guys, here's what we've said. We're talking about solutions, things that dissolve in water. And so if something dissolves in water and it is a substance that doesn't break into ions, that solution does not conduct electricity, and we call those things non-electrolytes. So what is an example of a substance that does this? Really simple example. I think it'll help you if you write it down. Sugar. Does sugar dissolve in water? Absolutely. If it didn't, we wouldn't have soda and candy and all the other things that we do with sugar water. So guys, sugar definitely dissolves in water, but when sugar dissolves in water, it does not break into ions, and therefore it doesn't conduct electricity. So if you were to take a bath in sugar water, you could drop your hairdryer in there and you'd be fine. Please don't try that, but in theory, it's the case. Sugar dissolves in water. That would be nasty. I think my wife does that, though. Don't they have like sugar scrubs? That's gross. Anyway, so if you decide, so guys, does sugar dissolve in water? Yes. Does it conduct electricity? No. Brandon, go ahead, but keep us on target.
Yeah. So
Catherine, I see it.
if it's molecular, so it dissolves not ionic, so it doesn't have a charge when it breaks apart.
Correct. And I'm going to show you pictures of this in just a second.
So how does water hold it apart?
Let me show you the pictures. So let me try this. If you're right now going, wait, I'm not quite, let's do, well, we'll try these questions, but what I may have to say to you is let me show you the animations, and then I think it'll bring this together for you conceptually. But let's try. Go ahead.
I had almost.
Go ahead.
Okay, so you know how, I know whenever stuff is like goes in water, it's connected. Is that because there's other stuff that's connected? Did you say water?
What was the C word that did you say connected? Say it, so, okay, say it again.
You know how when like if you put it like a toaster or something and then like electric shocks the water and it's connected?
And you die?
Yeah.
Right.
Is it because it's not like pure?
Exactly, because the water that comes out of our tap is so full of minerals that it's the minerals that conducts the electricity. It's not the water itself. Yeah, yeah, that's the difference. So guys, let's do this. If you're still sort of, pardon the pun, swimming in this, allow me to define the other term, which is electrolyte. Then I'll show you animations, and I think this will bring this together better. So non-electrolytes, do they dissolve in water? Yes. Do they conduct electricity when they dissolve in water? No. Why not? Because they don't break apart into ions when they dissolve. Okay, I'll show you an animation in a minute. Let me show you the other side of this. These are what are called electrolytes. Do electrolytes dissolve in water? Yes. But when electrolytes dissolve in water, they form ions in solution. And these ions conduct electricity. Examples of these? Salts. Oh gosh. Sorry, that was 2 clicks for the price of 1. Examples of these are salts, or if you just want to say table salt, that's fine. So now the question becomes, how can that be? How is it that some things, the non-electrolytes, can dissolve in water but not ionize, therefore they don't conduct, and other things, the electrolytes, dissolve in water and do ionize, and therefore they do conduct? Well, guys, it all comes down to how dissolving works. Are you all caught up? You guys okay? Okay, so guys, let me share this with you. This is obviously an animation and not a simulation. We'll talk at great length about the difference. Animations are cartoons. Simulations are actually computer representations of how things really happen. This is an animation. Okay, so here we have a water molecule. Hopefully you remember that water molecules are bent. Oxygen is more electronegative than hydrogen, so these molecules are polar. Because the oxygen is more electronegative than the hydrogen, these molecules are polar in this direction. The electrons pool towards the more electronegative oxygen, so this is polar in that direction. It makes them function quite literally like little magnets. They stick to each other, intermolecular forces. That's what holds them together as a liquid. When they boil, those intermolecular forces are overcome and they turn into a gas. That's also what allows them to dissolve things. When water dissolves salt and sugar and things like that, these polar molecules are attracted to the salt and the sugar, and it allows it to pull them apart. So here we go. Did you see the cube drop in? Would you like to see it again? There it goes. Oh, just wait. That's salt. So zooming in. Oh, yeah. So guys, not bad, right? They even got the colors right. Green is sodium, gray is chlorine, just like the crystal that I showed you before. But realize, really,
Okay, it doesn't matter.
you understand. So guys, notice then as the water molecules come in, these water molecules, because they are polar, these polar water molecules have negative and positive ends. Those water molecules are attracted to the positive and negative ions in the salt crystal, and they come along and they rip it apart. Notice that as they do, the negative dipole of the oxygen is attracted to the positive sodium, and the positive dipole of the hydrogens, which technically should be white, are attracted to the negative chlorines. And these molecules surround these ions and carry them off into solution. Notice that as they do, we are now creating mobile charged particles. Notice that this had charged particles as a crystal, salt, but solid salt does not conduct electricity. If you have a beaker full of solid salt, current can't flow through that because the sodiums and chlorines are locked in position. It takes them being dissolved and therefore mobile for this to conduct electricity. The water molecules come along, tear this thing apart, and we end up with a substance that conducts. You get the idea? Okay, so electrolyte or non-electrolyte? That is an electrolyte. As it dissolves, it creates charged particles. You guys okay? Okay, so now let's jump over here and look at sugar. As sugar goes into water, the difference is this. Now, instead of having positive sodiums and negative chlorines, what we actually have here are big organic molecules. C12H22O11 in this case. This is table sugar. And so guys, each of these molecules occupies one of these points in the crystal. So it's not like we've got alternating carbons and hydrogens and oxygens. Each of these points in a sugar crystal represents a big old honkin' sugar molecule. Now the trick is that these sugar molecules have little points of polarity on them. They're not charged, but they do have points of polarity just like water does. So when the water molecules approach the sugar, So as the water molecules approach the sugar, what ends up happening is the water molecules are attracted to the sugar molecules. But look at what happens. When the water molecules carry away the sugar molecules, you'll notice that the sugar molecules are not breaking apart. They are breaking away from each other, but the carbons, hydrogens, and oxygens are not breaking apart. So the covalent bonds inside the molecules don't fail. What does fail are the intermolecular forces between those molecules. And so as the water molecules go away, they go away intact as uncharged molecules, and consequently this can't conduct electricity. Do you see the distinction? Okay, so guys, here's where we are right now. We now understand that when stuff dissolves in water, it can either dissolve as an electrolyte or a non-electrolyte. Do non-electrolytes dissolve in water? Yes, but what don't they do when they dissolve? Break apart, therefore no charged particles, no conduction. And then on the other hand, guys, electrolytes not only break apart, when they break apart, they break into ions. Those conduct electricity, and that's why we call them electrolytes. Questions on non-electrolytes and electrolytes?
Does sugar not form carbon chains?
Those are the carbon chains. We just didn't draw them all out.
How does it perfectly break the carbon chain into
It doesn't. So the idea is that if you want to think of that as the carbon chain, the idea here is that each one of these is representative of one of those carbon chains. But the chaining doesn't extend between the molecules. You've got an isolated carbon chain, and it's actually really a circle, but you've got an isolated carbon chain, and each one of those is an independent molecule. And the thing that holds these molecules together are intermolecular forces. So you've got covalent bonds inside the molecules and then intermolecular forces between the molecules. Is that okay? Go ahead, Catherine. Mm-hmm. Exactly. Correct. So Na stays positive, Cl stays. What if it was copper 2 chloride? Then copper would stay +2, chlorine would stay. Their charges don't change. Yep. Is that okay?
Yeah, and then, sorry, I have one more.
No.
Even like, so you know how the like positive part, okay, so how the sodium's positive, so then the negative part in the water was like attracted to it, right?
Yes, the negative dipole, correct.
So
Uh-huh.
then, that doesn't like make it.
It doesn't neutralize it. No, it's an attraction, but it's not a bond. Yeah. Go ahead.
So if the NaCl is attracted together, how does the water tear them apart?
So the answer is going to, so the question on the table is, how does water do this? And the answer is by chance. So the water molecules, if you could look inside a beaker of water, those water molecules are moving randomly at hundreds of miles an hour, and they have kinetic energy. When they slam up against the salt crystal that we've introduced into the solution, they transfer energy to the salt, which actually causes these bonds to break, allowing for the attraction that carries them off. And we're going to look at that. We're going to actually quantify that mathematically in the next unit. So, you guys good? All right, so now guys, here's what we're going to do. We are now going to talk about types of electrolytes. Let that sink in for a second. So what does it mean to be an electrolyte? Does it dissolve? Yes. Does it break into ions? Yes. Does it conduct electricity? Yes. Okay, but what you're going to find out is that within that subset, and now we're thinking salts, right? Salts are electrolytes. You're going to find out that there's two types. One of these are what are called strong electrolytes. And guys, let's just clear this up right now. When you think of strong, you think of tough and you're strong, you're good, you're dangerous, whatever. You're strong. Guys, in chemistry, that's not what strong means. It means complete. Guys, underline the word completely. That's all that, in chemistry, that's all that strong means is complete. This is going to be really important when we talk about acids and bases on Wednesday. So guys, strong just means complete. So if you've got a strong electrolyte, it simply means that it completely ionizes in water. As a result, they are strong conductors of electricity. You know, I don't even want to use strong there because that's going to freak you out. They are good. These are good conductors of electricity. Now guys, as you would guess, if they're strong electrolytes, they're also weak electrolytes. Weak electrolytes only partially ionize in water. Instead of completely breaking apart, these things reach an equilibrium between their ions and they're non-ionized particles. And guys, we are not going to go into greater depth with that right now. We will when we get into weak and strong acids and bases on Wednesday. But these things are weak conductors of electricity. So guys, here's what we've said. Under this heading of electrolytes, which are things that break down into ions and therefore conduct electricity, some substances do that completely. When they dissolve, all of them break apart. Those are called strong electrolytes. Then there's another category of electrolytes where everything dissolves. And guys, you got to hear this. Everything dissolves, but not everything breaks apart. So it's not like some of it dissolves and some of it doesn't. It all dissolves, but not all of it breaks apart. Some of it stays together, some of it breaks apart. Those are what are called weak electrolytes. Now guys, you understand at some superficial level this idea. What you need to know right now is what are examples of substances that do these things. So let me give this to you. So guys, strong electrolytes. What substances are strong electrolytes? Well, you already know one. What is it? Salts. Guys, ionic substances, which we call salts, are strong electrolytes. So if a salt dissolves in water, it's a strong electrolyte. Which salts don't dissolve in water? That's why you know the solubility rules. And those precipitate. But guys, that's not it. There are other substances that are strong electrolytes. Another one are the strong bases. Technically, this is redundant because all the strong bases, for those of you that actually passed the quiz, all of the strong bases are hydroxide salts. So it's sort of redundant to the previous point. But then, guys, there's another class of substances that are strong electrolytes, the strong acids. HCl, HBr, HI, HNO3, H2SO4, those, HCl3, HClO4. Because here's the thing that's interesting. Those are not salts. They're molecules. All of the strong acids are actually molecular before they dissolve in water and become acids. So those are your strong electrolytes. Now, what about your weak electrolytes? Well, guys, your weak electrolytes include weak acids, weak bases, including NH3 and others, and then partly soluble salts. Guys, it turns out there are some salts that dissolve a little bit into water. We're not going to worry about these until chapter 17 back in March. But just understand, so you don't call me a liar later, there are salts that partly dissolve in water. We just won't worry about them until around spring break. Yeah.
Strong acids and strong bases.
And that's what makes them strong. Yep. Guys, okay?
So you said it totally dissolves, it doesn't totally ionize.
Let me show you.
Is that the same as sugar?
No, because sugar dissolves and doesn't ionize at all.
Well, I mean, parts of it are like sugar, other parts ionize.
Right, so it's as if it dissolves like sugar, but then some of those molecules fall apart. Not all of them, but I'll show you an example. So guys, you okay? Let me show you an animation. Strong and weak electrolytes.
Hydrogen chloride is a colorless gas, which is...
So guys, this is hydrochloric acid in its molecular form. We talked about this when we were going through the stock room back on Tuesday. Guys, all of the strong acids are actually gases in their molecular forms. You can actually buy a tank of hydrogen chloride gas. Understand that when the hydrogen's bonded to the chlorine, it's not an acid. It has to react with water first. So,
soluble in water and benzene.
So what we've got here is a conductivity apparatus. And let me explain to you the way this works. So the way this goes is we've got a power supply, and I know this is blurry because I zoomed, but we've got a wire that goes into a beaker of water. And then coming out of that beaker of water is another wire that's hooked up to a light bulb. And then all of this is hooked to a power supply. So right now, there's nothing inside of this beaker. If I remember correctly, there's nothing inside this beaker, so the circuit is open. Now, what's going to happen when they dump water into here? Check it out.
First, pure water is poured into a beaker.
So guys, when they dump the pure water into the beaker, why is the bulb not lighting? Why is current not being transferred? Exactly, water can't conduct electricity because it doesn't contain ions. That's what we've been saying about water all along. It doesn't conduct.
Water has a very low conductivity, and the bulb remains unlit. When
Now, guys, what they're doing is they are bubbling HCl, hydrochloric acid gas, through the water. As it does the HCl dissolve? Yes, but it doesn't just dissolve, it ionizes. And when it ionizes, it breaks into positive hydrogen and negative chlorine. And what does the positive hydrogen and negative chlorine do? Conducts electricity, and the light bulb lights up.
hydrogen chloride gas passes into the water, it dissolves, and the bulb shines very brightly, showing that the solution is conducting. Ions form because water behaves as a base, accepting protons from the hydrogen chloride.
We'll talk more about that later.
We get the hydronium ion and the chloride ion. In the last part of the
Okay,
experiment,
now what we're going to do is we're going to dump acetic acid into the beaker. And when we dump acetic acid into the beaker, is acetic acid a strong acid? How do you know? It's not one of the 7 you had to memorize. So any acid other than those 7 is weak.
we are
Guys,
using
look at
a
what
weak
happens.
acid, acetic acid. We pour 0.1 molar acetic acid into the beaker. And the light
And you'll notice that it only lights up partially. The question is why? And guys, let me explain to you what's going on. Inside this beaker, we actually have billions of these molecules. And guys, those molecules, acetic acid molecules, remember when you had to memorize that last year? Guys, those molecules are very soluble in water. So this stuff dissolves like crazy. But the trick is this is a weak electrolyte. You can see that the light doesn't light up very well. So does acetic acid dissolve in water? Yeah, really, really well. But the difference is this: when it dissolves, not all of these molecules break apart. Actually, most of these molecules stay like this, but some of them will do this. Some of them break apart into ions. Not very many. When they break, they actually break right here at this bond, and they form acetate and protons, hydrogen ions. But guys, not many of them do that. But the ones that do this, because they create ions, those conduct electricity. But because they don't all break apart, we call this a weak electrolyte and not a strong electrolyte, because they all don't break down. Does that make sense? Go ahead.
So the acids and bases, how come some break apart well and others don't?
Chapter 16. We're going to go over all of it. Yeah, oh yeah. Well, March. But yeah, we'll talk. Go ahead. Yeah, why does it? Absolutely. You'll find out that it's because of that's the weakest bond in the molecule, and that's where it'll break. But again, we'll talk about that in March. Yep. You guys understand weak electrolytes? Okay. So guys, we've got one more thing to do. We are now going to, now that we understand weak electrolytes, strong electrolytes, and non-electrolytes, what we're going to do now is we're going to wrap up today by talking about precipitation reactions. So let's briefly write down some definitions, and then here's what's going to happen. If you printed the notes, I am going to abandon the notes in about 3 minutes. We are not going to look at the notes anymore, but everything that you're going to write down with me will be in the notes. So if you printed the notes, understand that everything that we're doing, we are covering. We're just not covering them in the notes, but it will all be covered. If you want to go back and look at the notes later, you can. So guys, when we talk about precipitation reactions, we're obviously talking about reactions that form precipitates. And when we talk about precipitates, we are talking about insoluble products of chemical reactions. Now guys, in order to figure out which products are insoluble, we obviously need to know solubility rules. We're going to give you the opportunity in just a minute to stress test your solubility rules and figure out whether or not they work. But guys, in the meantime, here's what we're going to do. Y'all caught up with me? You guys know this stuff, right? Don't write down stuff you already know. You know precipitates just don't dissolve. Okay. So guys, here's what you're going to find out. Most precipitation reactions are double displacement reactions. Double displacement reactions, we know. So here's what we're going to do. We're going to write and balance this reaction. And we're going to include subscripts. And guys, the reaction that we're going to do is this, but I'm actually going to cheat a little bit. This will work better. Let me copy and paste this. Go here, get rid of all of this, and move this up, and then stretch it so it's only on one line. There we go. Okay, so guys, we are going to write the balanced equation for this. So if you'd like to write this down with me, you certainly can do that. But guys, we are going to write the balanced equation for this. And why don't we just go ahead and do it now together? So it says 1 molar lead-2 nitrate reacts with 0.5 molar potassium iodide. Why did I give you the molarities? We don't need them. But guys, if we're given a molarity, what does that tell us? How much is dissolved in water? So we know it's aqueous. Little tricks like this are helpful. If you don't know the solubility rule that says lead-2 nitrate dissolves in water, you don't need it because it's got a molarity. Okay, so guys, what is lead-2 nitrate? PbNO3 2. This is reacting with Ki, which is potassium iodide. Now we need to know the subscripts for this. Solid, liquid, gas, or aqueous? Aqueous, because they have molarities, we know that they're dissolved in water, like so. Now guys, we need to predict our products. So guys, in order to predict our products, the lead hooks up with the iodine, lead's +2, iodine's -1, PBI 2, and then our other product will be KNO3. And then we need to balance it, 1 lead, 1 iodine, 2 potassiums, 2, and that balances. We will in a moment. Okay, so now guys, here's what I want you to do. Skip down 6 lines. And skipping down 6 lines, please draw 1, 2, 3 beakers, and an arrow. Okay, so guys, in the bottom left beaker, what we're going to do is we are going to draw what 1 molar lead-2 nitrate looks like in the bottle. And guys, we are going to leave out the water. So we're not going to represent the water. But if you were handed a bottle of 1 molar lead-2 nitrate, what is in the bottle? Because there's no lead-2 nitrate in there. What happens to lead-2 nitrate when it dissolves? It ionizes. How do you know that it ionizes? Because lead-2 nitrate is a salt. And if it dissolves, it has to ionize. It's a strong electrolyte. So guys, what does it break into? Well, it's going to break into leads with a 2+ charge. And what else? NO3s. NO3 has a -1 charge. But that's not quite right. How come? There's 2 of them. We okay? So guys, do something similar in the second beaker. What about Ki? What does it break into? We get potassiums and we get iodides. 1 of each. And because we have charged ions in each, and can you even picture the water molecules surrounding those atoms and polyatomics? These are both strong electrolytes. They conduct electricity. Okay, so guys, you're going to be doing this in lab. Next week, you are going to do about 30 precipitation and other aqueous reactions. Now guys, so the trick is this. Imagine doing this. So if you're going to react these things together, because that's what we're talking about, is reacting them together, you're literally going to take a bottle of lead 2 nitrate and a bottle of Ki and dump them together. But realize when you're dumping them together, you are not dumping together lead 2 nitrate and Ki. You're dumping together lead ions, nitrate ions, potassium ions, and iodide ions. Does that make sense? So let's put them all over here in this beaker. When you dump these together, you're dumping together lead ions, nitrate ions, let's do 2 of them, potassium ions, and iodide ions. You just lumped all of those buggers together in one beaker. Just dumped them together. Now the question is, what chemistry did they do? So guys, let's go up here, and this is what you were mentioning, Isabel, about subscripts. So now guys, and if you need to look at your little solubility cheat sheet, go ahead and do it. Guys, let's look at our solubility cheat sheet and figure out whether these dissolve in water. Does KNO3 dissolve in water? Yes. How do you know? Guys, 2 reasons. 1, all nitrates dissolve in water. 2nd, all group 1 containing salts dissolve in water. That definitely dissolves in water. Now guys, what about PBI2? Does it dissolve in water? It does not. All halogen-containing substances dissolve in water unless it's bonded to silver, lead, or mercury. But which form of lead? Lead plus 2. This does not dissolve in water. This is a solid. That's our precipitation reaction. So now guys, do this with me. Go down here and let's amend what we've got in this picture to figure out what is actually going to be in this beaker, because we now know that the lead and the iodide is not going to be floating around in solution. Where will it be? Do you see what I'm saying? Guys, we know that the lead iodide does not remain dissolved in solution. It's a precipitate, and where does it go? To the bottom. So literally what you're going to do is draw a pile, and you're going to put PBI2 down in the pile and cross it out of up here, because the PBI2 is on the bottom. It's a precipitate. Now guys, check this out. This is what we now understand. When we mix these 2 beakers together, we didn't start with this, we started with these. And when we mix them together, the lead from here and the iodide from there got together, and this isn't balanced, but it made PBI2, which was a precipitate. Here's the question. What did the nitrate do? Nothing. It didn't do any chemistry. Guys, the nitrate started dissolved and it ended up dissolved. The nitrate did not do any chemistry. What about the potassium? What did it do? Started dissolved, ended up dissolved. It didn't do anything either. The nitrate and the potassium didn't do any chemistry. There's a name for that, and you want to write this down. These are what are called spectators. Now, guys, here's what you've got to learn to do with this. And understand there's the possibility that the bell may ring. I'm going to ask you to give up 2 minutes of your lunch. Eventually, we're going to get this balanced. We need to figure out how to balance this idea that you guys ask a lot of questions with we need to get through material. We're going to need 2 minutes. So, guys, here's what we've got to learn to do. We've got to learn to take these equations and pare them down so that they don't represent the things that didn't do chemistry. So here's how we do this. Guys, as we go through this, did nitrate do any chemistry? No. So what I want you to do is cross it out. I'm going to do it in red. So guys, nitrate did not do any chemistry. We're going to cross it out. We should do this. Did lead do chemistry? Yeah. Did potassium do chemistry? No. So we're going to cross that out too. And we're actually going to cross it out on both sides. Now, guys, look at what's left. What's left is lead. But, guys, remember, lead started out dissolved in water. So its charge is +2. When these things dissolve in water, they take on charges. And you've got to remember, represent their charges. So lead is +2. And this reacted with 2 iodides. And when that happened, it formed PbI2, and that's a solid. Guys, that is the chemistry that took place in that beaker when you mix these two things together. Notice this. Your reactants have charges. Why do they have charges? They're dissolved in water. They're ionized in water. Notice your product does not have a charge. Why not? Because it's a solid sitting at the bottom of the beaker. Now, guys, this has a name. This is what is called a net ionic equation. And guys, for the rest of the year, whenever you write a chemical reaction, it will always be the net ionic equation. So you will figure out which things are doing chemistry, which things are spectators, get rid of the spectators, and only write down the things that are doing chemistry. They're called net ionic equations. Now, guys, here's the scoop. You'll obviously have practice in your homework. But guys, the way this works is there's lots of examples of, here's all the notes about what you just learned, net ionic equations. Here's your homework. These are all out of chapter 4. When I see you on Wednesday, we will grade this homework, and you have a chapter summary that's due to me for chapter 4. In second period, we'll get you guys into lab. When you're done writing this down, have a great lunch. And guys, if you need help on this along the way, if you're sitting down to do the homework tonight and you're like, oh my gosh, I'm not quite sure what was going on, I'd love to work with you. Swing by. I'm super available before and after school. So come by and say hey. But guys, when you're done writing this down, you're welcome to go.